I said stop, not God.
Oh, sorry.
If in doubt, read wrong.
All right, energy. It is definitely related to the way energy is used in everyday life. However, of course, we get a lot more picky about it. Technically, gasoline is a source of energy, oil, a source of energy, biomass, a source of energy. There are a lot of things a source of energy. A match is a source of energy. But we basically break energy up into three kinds: kinetic, potential, and rest. The textbook covers kinetic and potential. I don't know if it covers, I don't think it covers rest energy in chapter 7, but for completeness. Now, if we think about an object, all objects have some speed. Now, that speed might be 0, but they have a speed. So all objects have speed. All objects have some location. If it doesn't exist anywhere, then is it really an object? We'll get into those philosophical discussions later. Also realize we're dealing with classical mechanics here. So any of the really obscure exotic particles that we might have now, or any idea that an object could be in more than one place at once, is not really part of this. So they all have a location. And classical physics, they all have mass. Now it turns out that there are some objects that do not have mass, in which case rest energy is off the table for them. So if all objects have a speed, location, and a mass, there's an energy associated with each of those. Speed deals with kinetic. Location deals with potential. And rest deals with the mass. Now the symbol for kinetic energy, I know it's going to shock you. If you wonder where it comes from, just ask. The symbol for kinetic energy is a capital K. The symbol for, now I think the textbooks use KE, or he writes out kinetic energy. Just recognize, I'm just going to use the letter capital K to represent kinetic energy. I guess I'll throw in the energy part. Potential energy, now this is one that a lot of people like using PE or something like that. I'm not going to break my habits. Capital U. And I believe it comes from the German, but I'm not 100% sure of that one. But if you get far enough in physics, capital U and capital D is often used as well. And then rest energy, just needs a mark. Now there is a PowerPoint where I go through the derivation about the formula I'm about to give you, where it comes from. I'm not going to go through the derivation unless there's a huge groundswell for me to do the derivation. I know half of you are thinking, yes, please do it, but I will refrain for right now. So I do explain where this comes from in one of the PowerPoint. I think in the PowerPoint, or it might be in the video also. But the formula, 1/2 mv squared, because it does relate to speed. More specifically, it deals with speed squared. Now, there are a lot of formulas that would be really nice if you know. This is a formula that I do expect you to know cold. And we're going to run through this right now. I'm going to do a quick little story first. When I first started doing consulting with what was Anderson Consulting at the time, we were going through the basic training, and we were all doing some coding, and these people came into the room and said, all right, everybody up. And there were some people who were hesitant, and they stopped and said, we are serious, everybody get up now. So we got up and did jumping jacks. So, I am serious. I want every single one of you to do this, what I'm about to ask you to do. If I ask you, what is the formula for kinetic energy? I expect you to respond 1/2 mv squared. Let's give it a shot. Looking for the chorus of angels, a single clear sound coming from you. What's the formula for kinetic energy?
1/2 mv squared.
That was nice. Thank you. 30 years from now, as my memory is even worse than it is now, and I run across you in the street, I should be able to ask you, what's the formula for kinetic energy? And I do expect you to know it. Yeah, well, let's just assume I'm still around then. All right. Potential energy. If I ask you, what's the formula for potential energy? Doesn't have to be in unison, but I do expect the response of, which one? There is one formula for kinetic energy. There are a lot of formulas for potential energy. The textbook makes it seem like there's one formula, but there are a lot of formulas for potential energy. So, not necessarily in unison. You could do this in rounds. You could do this, some beautiful choral arrangements we could try right now. What's the formula for potential energy?
Which one?
There we go. All right, excellent. Potential energy formula depends upon what is the conservative force. So this gets into two types of forces. Conservative, not capitalized for any particular reason, and non-conservative. I think I spelled this right. So this obviously is not a political leaning. This deals with whether something is conserved or not. Considering the topic, what do you suppose conservative forces conserve?
Energy.
Excellent. Yes. Conservative forces conserve energy. Now there is a formal mathematical calculus-based definition for it. I find for most classes, even for the calculus-based class, I do the same thing. It's easier just to give you the list of all the conservative forces we have dealt with up till now. That's it. Those are all the conservative forces we have done. Everything else we've done is non-conservative. Up to here. There is, F sub g is the force due to gravity. Generally use this for the generalized formula that we will see in chapter 9, I think. And this is weight, which is just a special case. There are two more conservative forces that we potentially will deal with. There is basically elastic force. I'm using S for spring instead of E for I use E for electricity. But force from a spring, an ideal spring, is a conservative force. And probably won't get to it, but if occasionally get to electric force. Magnetic force is also conservative, but we definitely will not get there.
So like for the FS, you said you're using the FS, but for the force, the other force, what was it?
You know, like tension,
No,
normal?
force, elastic, I think you said?
Yeah, I asked for spring force, like if I had a slinky and just moved it up and down, it's really an elastic force. An ideal elastic material, anything that will stretch and then come back to its original place, ideally, those would be conservative forces.
Okay. And how would you write down force elastic?
I would just use F sub S for spring.
The-
I will sometimes just call it spring force, but it really applies to more than just springs.
So just use FS for anything elastic?
Yes,
Okay.
yeah. Thought you were asking something.
I think he was thinking of the bottom one is electric force.
Yes, that E right there is for electric. All right, so I'm gonna put a little F sub C here for conservative force. I guess later, let me write out con for at least conservative force, because F sub C in chapter 8 is for centripetal. So the conservative force, if I'm dealing with weight, the potential energy formula is mgh plus a constant. Generally, the plus constant is ignored. If the conservative force is the generalized gravitational force, which we haven't gotten to yet, the formula for this would be negative big G mass 1 mass 2 over R. That will make more sense later, I hope. If we're dealing with a spring force, the formula is 1/2 lowercase k, technically delta x squared. This k right here is known as the spring constant. Oh, yeah. Plus constant, plus constant. Any of these, you can always add a constant.
So when you say a constant, what is the constant number that we would use?
It depends upon how you define 0. Just like we got to decide the positive and negative directions with vectors, with this we get to decide where we want potential energy to be equal to 0. And so that constant is just to give us the room to do that. I'll do an example later. And then electric. If we're dealing with electric force, the potential energy formula is K sub C, Q1, Q2 over R. That's supposed to be a K there. Now, I'll present this up here just again to emphasize the fact that if you're dealing with potential energy, there's several formulas for it.
What is that last one? The last formula?
K sub C, or Coulomb's constant, times Q1, Q2 over R. Q is representing the charge, so I have two charges that I have a force between them. If they're the same charge, they're repelled. If they're opposite charges, they're attracted.
And K is spring constant?
This K is spring constant, this K right here is Coulomb's constant. Again, we've run out of letters, we have to read. Lydia?
So just so that I'm understanding this right, whichever conservative force you have determines the equation for potential energy?
Absolutely.
So this is all potential energy?
Those are all potential energy formulas. We will not deal with all of them probably, but I just, again, emphasizing the fact that there's more than one formula. Other questions before we talk about rest energy, and then probably just talk probably 2 minutes on rest energy, and then we'll ignore it for the rest of the time.
What formula is used the most?
In this course, the first one, MGH.
Okay.
What does it say right beside the MGH plus what?
Plus constant.
Oh.
I can add a constant. I can add a constant to anything, any of these formulas, just so long as it's the same constant consistently throughout a problem. Kimberly?
And what is the F and the W?
The
On the
W over there.
Yeah.
These are the conservative forces. W stands for weight, just like we did before. F sub G is general gravitational force. F sub S is the spring force or elastic force, and this is electric force.
Oh. So you just put the F with con to say F conservative?
Yes.
Oh.
Each conservative force has a potential energy formula.
Oh.
Other questions at the moment? Oh, rest energy. Most of you know the formula for rest energy, although if I just said, hey, write down the formula for rest energy, I suspect that a good number of you would not know what to write. But I can get you started. E equals the formula for this is M, one slight difference, M sub 0 C squared. M sub 0 versus M. M sub 0 is the rest mass.
Is that the only equation for us?
Yep. Rest mass is, actually, any mass that you've ever measured in there, you're finding the rest mass. We don't call it that, but we just call it the mass. The mass differentiates from rest mass for practical purposes once you start getting around 30 million meters a second, which is not within the realm of most of our experiences, I'm assuming. I'm making an assumption about your home life, I don't know. So we got Lydia and Kimberly both have hands up. I can't remember which was first. Kimberly.
Is it M-E or M-O?
The subscript right there is a 0.
Okay.
So do we ever have to worry about, like, finding a different mass, if it's
No.
a given mass? Okay.
We don't in this class.
Okay.
This is the people who worry about that in physics 252 and physics 152 is where you would tackle that. Just a quick example. So how much energy is in me right now? If we could somehow convert me into pure energy, how much could we get out of that? Well, we got a formula right there which says how much energy is in me. So my energy, my mass is, I'll just make the math easy and I'll just say 100 kilograms. The speed of light, 3 times 10 to the 8 meters per second.
What?
300 million meters a second.
Why you gotta do that?
That's what the formula is. This rest mass times the C right here, that's the speed of light.
Oh.
Sorry, I fell into my own little world there. Everybody knows what C is. There is an exact number. This is close enough for what we're doing. Squared. So that's 9 times 10 to the 16, 17, 9 times 10 to the 18th.
So whenever you're solving for rest energy, really all you have to do is just insert the mass, because light energy doesn't change, or,
Well, the speed of light is a constant.
right?
So, and then units. Let's take a look at units here. I have kilograms times, I have a meter per second here, but I'm squaring it, so that's times meters squared per second squared. So I have a kilogram meter squared per second squared, and the physicists looked at that and they said, oh, God, do I have to write in all that stuff? And so they said, no, you don't. Let's see if we can find a physicist who kind of worked in this area, and we can call a unit after him, and they did that. So a kilogram, meter squared per second squared, is a joule. Anyone want to take a wild guess at the name of the physicist that they're honoring? Amazing the way that works out.
What y'all say? The name?
Yeah.
Oh, that was his
Joule.
name?
Yeah.
What's his first name?
I think it's Robert.
Oh. Is it Robert?
I actually do think it is Robert, but I could be wrong on that.
You said it too
Oh, wait.
quick.
Prescott. Robert Prescott. I think his middle name is Prescott.
Okay.
It'll hit me in the middle of the night and I'll give you a call. All right, so that's what a joule is. So joule is the unit that is going to be used for energy. That's the SI unit. That's the standard international unit. Foot pounds is also a unit in, I guess, our system. British thermal units, BTUs, is also a unit for energy. Calories is also a unit of energy. All right. So There's a whole lot of energy into me. Now, being able to convert me into pure energy is very difficult. If you think about a match, if I take a match and I strike it, well, I have a match, I find its mass incredibly precise, mass of a match. I then light it, capture any ash that there happened to be, and so then I find the mass of all the ash and the match itself, and there's going to be a difference in the mass. Mass was lost. That mass, if I find the difference in the mass, multiply times the speed of light squared, that's how much energy was released. Not a heck of a lot from a single match, but there's still a loss there. And I think now I'm finished talking about rest mass, or rest energy. F sub g, yeah, force due to gravity.
Okay, so is that negative G?
Yes,
Okay.
that's a capital G. And the fact that it's capital G is important, it's not a lowercase g.
Thank you.
Yep. And one of the reasons I'm picky about when you say gravity is involved, and I ask you to be more specific, that's because uppercase G is known as the gravitational constant. Lowercase g is the acceleration due to gravity. This is the force due to gravity, and that's also the force due to gravity. Those are the three major things that I've heard students call the exact same thing, gravity. That's why they are not the same. They're definitely all related to each other, but they are not all the same. One other thing that will come in handy for the lab is that there's something else called work. And the reason I don't use capital W for weight is as capital W is for work. There is conservative work and non-conservative work. Conservative work conserves energy. Non-conservative work does not. From this, there are three work-energy relationships. The total work done, I guess I need to define work, but the total work done is equal to the change in kinetic energy. This is also known as the work-energy theorem. I think it's mislabeled because this is true because we define work and kinetic energy so that this works.